Hello, class. Topic 18 is on forced harmonic motion. Suppose a 500-gram mass is attached to a spring with a stiffness coefficient of 8 newtons per meter. An external force of 3 sine 2t newtons is applied, but no damping force is present. The mass is pulled 1 meter above spring mass equilibrium and given an upward speed of 1 meters per second. Find the model for the motion of the mass as a function of time. Okay, so we have no damping force, so we know mu is 0. And the mass is 500 grams. However, the m unit for the mass needs to be in kilograms. So we do want to convert 500 grams to kilograms. That's going to be a half of a kilogram. So mass equals 1/2 a kilogram. Mu is 0. The K is the spring stiffness coefficient, which is 8 newtons per meter. I'll just put the 8 there. And our F of t is the forcing function. So we have an external force that's being applied. That's our F of t. And this, of course, is going to create an inhomogeneous differential equation. So now rewriting the differential equation, 1/2 y double prime plus 8y is equal to 3 sine 2t. And this is the differential equation we want to solve. I'm going to use the method of undetermined coefficients to solve this. But first of all, we need to find what the linearly independent solutions to the homogeneous version of this differential equation would be. Also, I don't like the fraction, so I'm going to go ahead and double everything to begin. So we have y double prime plus 16y is equal to 6 sine 2t. And this is the differential equation I'm going to focus on. The characteristic polynomial would be lambda squared plus 16 is equal to 0. And this has two roots. Lambda equals plus or minus 4i, giving us two linearly independent solutions. Y1 will be cosine of 4t, and y2 will be sine of 4t. Now look to the forcing function. The forcing function is not equal, or is not a multiple of either of these. And so we are safe to construct you may want to refer to your notes, by the way, from the method of undetermined coefficients to make sure you're setting up your particular solution correctly. But in this case here, we're going to call our particular solution will be y sub f. I'm using f instead of g because our forcing function is now using f. And we want it to be of the form, we have a 0-degree polynomial times a sine 2t. So we need a 0-degree polynomial, which is that's arbitrary, so an a, in other words, times a, and it doesn't matter what I write here first, but let's go with sine 2t first, it doesn't matter. Sine 2t plus an arbitrary polynomial of degree 0, so a constant b, times cosine of 2t. Now we're going to take this template, if you will, for the particular solution to the inhomogeneous differential equation and plug it into this differential equation and see if we can determine what the coefficients a and b need to be. So I'll have to do a couple derivatives here. So y sub f prime. The first derivative is going to be, using the chain rule, so we get 2a cosine 2t, and then minus 2b sine 2t. And then the second derivative, y double prime, chain rule applies again. We're going to get negative 4a sine 2t, and then minus 4b cosine 2t. Now I want to plug these into the differential equation and try to determine what a and b are. I'll do that work up here on the left, or on the right, sorry, in this space here. I'm going to take y double prime, this expression right here, and plug it in for y double prime right there. So I'm focusing on this differential equation, substitute y double prime with this. So I'm just going to copy paste this. Okay, so there's my y double prime. And to that, next I'm focusing on plus 16 times y, and for y get substituted in this. So we're going to have plus 16. Let me put parentheses around this first just so we can see it as its own entity. Let me move this over. There we go. And let me get this out of the way. Already running out of space. It's a lot of writing I have to do here. Maybe I should have zoomed in and written a little bit smaller. Let's grab now this y. Paste that up there. And we want all of this to be equal to, looking at the differential equation right here, to be equal to 6 sine 2t. Okay, we got that fit in there okay. And now we're going to do a lot of distributing and grouping terms together. I'm going to try to do a lot of this in as few steps as possible to minimize time writing. So I'm going to focus on, I'm going to underline all the terms that have a sign attached to it. Underline them in red, so those two. And then all the ones that have cosine attached. So I'm going to do some distributing and factoring all at the same time. I'm going to gather the sine terms together and factor out the sine. So we have a negative 4a, and then we're going to have a plus 16a. And this would be times the sine 2t. Now focusing on the orange, the coefficients would be negative 4b, and then plus 16b. Don't forget to distribute. This 16 here needs to distribute to that b. So 16b, and that's going to be times cosine 2t, and this needs to be equal to 6 sine 2t. All right, well this simplifies nicely to just a clean 12a sine 2t plus a 12b cosine 2t has to be equal to 6 sine 2t. And from this we can see what a and b have to be pretty quickly. A has to be 1/2. And let me write that better. And b has to be 0 because there is no cosine term on the right side of this equation. So this allows me to create a general solution. We'll start with the particular, which is going to be, looking back at this here, use the correct a's, 1/2, and the b is 0. So I'm going to rewrite that with those correct coefficients. So we just really have 1/2 sine 2t. This is our particular solution. To that, we're going to add a c1 times our y1, which is cosine 4t, and then plus a c2 times our y2, which is sine 4t. And here's our general solution. Now we want to take our initial conditions. I'm going to have to do a derivative and apply our initial conditions to see if we can figure out what c1 and c2 are. So let's go with y prime is equal to the derivative of the particular portion of our general solution is just going to be cosine 2t. Then we're going to have minus 4c1 sine 4t. That's a 4. And then plus 4c2 cosine 4t. Just get rid of that. And our initial conditions. We know that, let's look back up here, the mass is pulled 1 meter above spring mass equilibrium. So make sure we're in meters, which we are. If this had been in centimeters or something, we would have had to do a conversion. But this is 1 meter above spring mass. So that's going to be a positive 1. If it was below, it'd be negative 1. So we know that positive 1 is equal to y of 0. So we just got to plug 0 into our general solution right here. 0 is going to kill the sine term and this sine term, leaving only this middle term, and the cosine of 0 is 1. So we get out of this c1 all by itself. c1 is just 1. Okay, now let's look at the other part of our initial condition. We were given an upward speed of 1 meter per second. So velocities going up are positive, velocities going down are negative. So it's going to be a positive 1 will be our y prime at time 0. So plugging in 0 into y prime. So this time, this term is going to 0 out. Cosine of 0 is a 1, so we get a 1 to begin. Cosine of 0, that's a 1, so we get a plus 4c2. And when we solve this, we get c1 is 1. That's just given obviously in the first equation. And then solve the second one for c2. Notice we're going to get c2 has to be 0. So this gives us a final particular solution of y is equal to 1/2 sine 2t plus 1 times cosine 4t, so just cosine 4t, and then plus 0 times sine 4t, so 0 kills that term, and we have a particular solution. So this is going to be the model for the motion of this mass as a function of time. Now we're going to go over to Desmos and graph it. And I've already typed this equation in so we can just see it. And you can notice that we have this sort of irregular sinusoidal function. It's because we're combining a sine and a cosine of different arguments. They have different individual frequencies, and so you get this strangely shaped sinusoidal curve. And remember, there was no dampening in this, so that's why we're seeing a pattern emerge, but that pattern emerged. The pattern emerged immediately, and that pattern just repeated forever. As time goes on to infinity, we just continue with the same function. Notice that initially, our object started at a height of 1 meter above the equilibrium, and it had an upward speed of 1 meter per second. So if I did a tangent line, y equals a slope of 1, so 1 times x plus its initial position, we should expect to see, as we do here, that the line that I just made here, let's make it in purple, is, oops, that's not what I wanted to do, zoom in, there we go, is tangent to the curve at its original point. So we started off on that trajectory, but then all the forces involved set in motion this harmonic motion. I think that's all we were supposed to do on this one here. Okay, let's go to the next problem. A 500-gram mass is attached to a spring with a stiffness coefficient of 5 newtons per meter and a damping coefficient of 1 newton second per meter. So now we have damping involved. Also, an external force of 2 cosine t newtons is applied. Find the general solution to the corresponding ODE. Notice this doesn't say find the model for the motion, so just the general solution. We'll actually use the next slide to finish this problem and find the specific model for motion. Okay, so the mass, again, is 500 grams. Convert that to kilograms. So we have 1/2 kilogram is our m times y double prime. Our mu is 1 newton second per meter, so mu is just 1, so just plus y prime. And then the k is the 5 newtons per meter, so plus 5y. And this time we have an external force of 2 cosine t. Again, I'm going to double everything to get rid of the fraction, just make everything have integers. So y double prime plus 2y prime plus 10y is equal to 4 cosine t. This is the differential equation I'm going to try to solve. First we want to, again, it's inhomogeneous because we have a non-zero forcing function over here, and also I'm going to be using the method, again, of undetermined coefficients. But first we need to find the characteristic polynomial from this part and figure out what the linearly independent solutions to the homogeneous version of this differential equation would be. So we have lambda squared plus 2 lambda plus 10 is equal to 0. Okay, so we're going to apply the quadratic formula next. So we have lambda must be equal to negative b, so negative 2, plus or minus the square root of b squared, so 4 minus 4ac, that's going to be minus 40 all over 2. And when you simplify this, we're going to get negative 1 plus or minus 3i. So that tells me that my y1 and my y2, y1 will be e to the negative t cosine 3t, cosine of 3t, and the second linearly independent solution is going to be e to the negative t sine 3t. Now I want to go for the particular solution given that we have an inhomogeneous. So this cosine 4t does not match either of our independent solutions. It's independent from them, and so what we're going to be able to do is construct a particular solution y sub f by doing a 0th degree polynomial in the front that's arbitrary, so a times the sine of t plus a 0th degree polynomial that's arbitrary but different, so b times the cosine of t. You may want to refer to your notes for the method of undetermined coefficients to make sure that you're setting up this template correctly. So now we're going to use this and do a few derivatives and then plug it back into this differential equation right here to figure out what a and b have to be. So the first derivative, y sub f prime, is going to be simply a cosine t minus b sine t. And the second derivative, y double prime, will be negative a sine t minus b cosine t. Okay, now these get plugged into this derivative. or into this differential equation right here. I'm going to start with y double prime. So I'm going to just copy paste this. And there's y double prime. Then we're going to add to this 2 times y. Y is right here, so copy paste that. And then we're going to add to that plus 10, so that was 2 times y prime. Now we're doing 10 times y, and y is right here. And all of this should be equal to 4 cosine t. Let me move this over just slightly. Okay, so this becomes the equation I want to ultimately try to figure out what a and b are so that this turns out to be a true statement. All right, once again, I'm going to do all the gathering of the sine terms together. I'm going to underline all the sine terms, make sure they don't get missed. There's a sine term, here's a sine term, and here's a sine term. And then all of the cosine terms, I'm going to gather them together and factor out the sine and cosine. So let's start with the reds. All the coefficients of sine. So we have negative a is a coefficient, the first one. Don't forget to do your distributing. So this 2 and negative b have to multiply. So we have minus 2b. And over here we would have, plus 10a. And all of that is times sine of t. Plus, now let's do the greens. We have negative b to start. We have plus 2a, distributing the 2. And then plus 10b, distributing the 10. All of that is times cosine of t, and this has to equal to 4 cosine t. So I'm in a position now where I can equate coefficients. We know that there is no sine over here. So that means this part here must be 0. And equating, we have a 4 in front of the cosine, so this part here has to be 4. This is going to allow me to create my system of 2 equations with 2 unknowns. Let's write that system down. So looking at the first one here, that this has to equal 0. Combining some terms, we really have 9a minus 2b. So we have 9a minus 2b has to be 0. And then the second one, combine the b's here. We have 9b plus 2a. 9b, let me write them in order. Plus 2a. So I'm going to put the 2a first. 2a plus 9b has to be equal to 4. So this is our system that must be solved for a and b. I'm going to use elimination, and I'm going to eliminate the b's. So I'm actually going to adjust both equations. I'm going to multiply the top equation by 9, the bottom equation by 2, and then add them together. And this should eliminate our b's. So 9 times 9, so I have 81a plus 2 times 2a. So right now I'm just adding up the first columns. So we have 81a plus 4a, so we have 85a. Then we have negative 18b plus 18b, so the b's will cancel as we designed. And then we have 9 times 0 plus 4 times 2, so we just get a nice 8 here. That tells us a has to be 8 85ths. Now we want to find b, so I'm going to use the top equation to help us find b. Let's make that look like a 0. It looks kind of like a 6. That's a 0. And so we have 9 times a. Well, 9 times 8 85ths is 72 85ths. Minus 2b has to be 0. So add the 2b, divide by 2. So b has to be 36 85ths. Now I'm able to construct my general solution. Y is equal to... So we go back to our particular solution right here. We'll start with that. In fact, I'm going to be using all of these pieces right here. I'm just going to copy those and bring them down. See, I don't need to have these things written. Let me erase that stuff. Okay, so let's begin with our particular solution that gets put in place with the correct a and b. And a was the coefficient, as the 8 85ths. So we have 8 85ths of sine of t, and the b is 36 85ths. So there's the particular solution component. Let me move those a little bit closer together. Move that over slightly. In fact, let me, just so I can make sure I can fit all this in one spot, let me move this work up there. Lots of rearranging here in this little tiny bit of space. And then to this, I'm going to add the general arbitrary constant times the first linearly independent solution to the homogeneous, plus an arbitrary constant times the second solution to the homogeneous. And this becomes our general solution. Okay, now let's go to the last slide. The last slide is just a continuation, really, of the second task we just finished. Consider the previous task. Suppose that the mass is initially pulled up 1 meter above spring mass equilibrium and given an upward speed of 1 meter per second. So those are the same initial conditions as our first problem. Do the following. Find the model for the motion of the mass as a function of time. So here we got to go for the particular solution next. So let's go ahead and just copy this and bring that down. Okay. Now I want to do a first derivative. So we have y prime is equal to, let me zoom in a little bit here. So we have 8/85 cosine t minus 36/85 sine t. Now here we're going to have to do a product rule on this part and a product rule on this part. So we have plus c1, and now apply the product rule. The derivative of the first. The derivative of e to the negative t is negative e to the negative t times the second, plus the first, e to the negative t, times the derivative of cosine 3t, which is going to be negative 3. So we put subtraction 3 sine 3t. Plus c2 times, and we have to do the product rule here as well. Derivative of the first is negative e to the negative t times the second, plus the first times the derivative sine 3t, which is 3 cosine 3t. Okay, so there's our derivative. Now our initial conditions are the same. We still have y of 0 is going to be 1 meter, and y prime of 0 is also going to be 1 but meter per second. So we have 1 is equal to y of 0. So looking at this one here, plug 0 in for all the t's. Well, the sine t's are going to 0 out, and that's going to 0 out that one. So we're only going to have these two terms present still. Cosine of 0 is 1, e to the 0 is 1, and cosine of 0 is 1. So that's all 1 there, so we just get c1, and we get this fraction 36/85. So we have 36/85 plus c1. And if I just subtract now 36/85 from 1, we get c1 is equal to 49/85. Okay, now let's plug 0 into the derivative. I get 1 out of the derivative as well, so y prime of 0. And this time 0 is going to make that's going to 0 out, this is going to 0 out, and this is going to 0 out. Let's see, the things that don't 0 out are right here. So we have 8/85 to begin. Here we have a 1 right there and a 1 right here. So this is a negative 1 times c1, so minus c1. And then that's zeroed out. This is going to 0 away, but this is going to be a 1. This is going to be a 1, so we do have a 3 here, times a c2. So 3c2. And this is what we get when we plug 0 in to the derivative and set it equal to 1. Well, c1 is 49/85. So this winds up producing an equation. I'm going to write it here, yes. So we get 1 is equal to 8. Well, let me just plug this in and do the calculation. We have 49/85 is going to be able to go in right here. So 8 minus 49 is going to be negative 41/85. That was for me just combining these two. Then we have plus 3c2. I'm going to add this 81/45 to this side. So that's 85/85 plus 41. So we have 126/85 is equal to 3c2. Therefore, c2, divide that by 3. And it turns out that 126 is divisible by 3. We get 42. So we get 42/85 is c2. Okay, now I can write my particular. Let me just copy this. And we can replace c1 with 49/85 and replace c2 with 42/85. And we now have our model of motion. I'm going to go to Desmos next and reveal that graph. I already have it all typed in here. It's the second line. And here's the model of motion. Notice at first that there appears to be some irregularity, but then it seems to settle into a regular pattern. Now, why is this happening? Well, the initial perturbance, which is lifting the mass up to 1 meter above and then also giving it an initial velocity of 1 meter per second upwards, causes a disturbance to the system, but also there's a regular external force trying to act on the system. So it's going to take a moment for that perturbation to dampen, because remember there is dampening this time, unlike the very first example. And the damping will diminish those perturbations and negate them eventually, and we will settle into a regular harmonic motion that's a consequence of the regularity of the forcing function that's at play. In fact, if you look at the equation, analyze it as t goes to infinity. Well, any part that has an e to the negative t times these trig functions, those are going to approach 0. In fact, why don't we go ahead and say, indicate this. I'll put it in red. So this portion right here will approach 0 as t approaches infinity, because those exponentials will drown them out, zero them out. That's the dampening part. The dampening of the damping characteristic of the spring is going to kill this portion of our solution to the differential equation, which means we're going to settle into a function that looks more like this function. This is called the steady state. It's the part that's going to continue undisturbed even as time advances. As time advances, only these portions of our solution effectively, their effect becomes nullified. So our solution approaches the behavior of this function only. That's called the steady state. Now if I go in here and I graph only that portion, which is the line below, notice how initially we have sort of this oscillation around the steady state. We have a irregular harmonic motion occurring, but as the initial perturbation, as the initial disturbance to the system is dampened or damped, then that perturbation nullifies, becomes nothing, becomes inconsequential, and we settle into this steady state. And the steady state, this harmonic motion, is due to the fact that we have a external force acting in a harmonic manner on this system. So the final questions of this task were to next determine whether the mass settles into a steady state. The answer is yes, it does. You just look for the components that would drown out to 0 as t goes to infinity and remove them. And then whatever's left we call the steady state. And if so, find the amplitude, period, and frequency of the steady state. So frequency is something new that we are talking about. We haven't mentioned that yet. But amplitude and period. So our steady state is a combination of the sine and cosine function. So that's what we want to focus on. Let me go ahead and just copy that portion. Paste it over here. This is our steady state. And to find the amplitude of this steady state, we do the Pythagorean theorem on the coefficients of the sine and cosine functions. Now notice these have the same argument. So it is possible to write this instead as just a single trig function, and we're finding the amplitude of that single trig function by doing the Pythagorean theorem on the coefficients of the sine and cosine. This was discussed in the last unit on topic 17. And so we have the square root of 8/85, that needs to be squared, plus 36/85, that needs to be squared, and then we do the square root of all that, and we get approximately, and I did this in Desmos already, so we should have this calculated already, and it's about 0.43386. And this unit would be in meters. I'll show you that. Calculation was done right here in Desmos. You can see it already. What that means is that we settle into a sine wave that if you were to find one of its peaks, it'd be, about 0.4 3, 4 units above and also below. So that's our amplitude of the steady state. And the period of the steady state can be found by doing 2 pi divided by the coefficients of the t's. So the period is just going to be 2 pi divided by 1. So it's just going to be 2 pi, which if you decimalized 2 pi, we'd get about 6.28 or so. And this is measured in seconds. So the wave would repeat itself every 6.28 seconds. And finally, the frequency. Now, what is the frequency? The unit of the period is really seconds per wavelength. I'll just say seconds per wave. That's how you want to think of the period. It's how many seconds it takes for one wave to complete its cycle. And frequency is how many waves there are per second. So in other words, you just have to do the reciprocal. All right, frequency is going to be the reciprocal of the period because we just want the reciprocal unit. We want waves per second. So we do 1 over 2 pi. Let's go over here. And oops, I'm going to have 2 pi there. Let's do 1 divided by 2 pi next. And we can see that 1 divided by 2 pi in decimal form is about 0.159, we'll say. 0.159, and this would be waves per second. Now, the unit of frequency is also a hertz, so it's 0.159 Hz, which is short for hertz, which is effectively wavelengths per second. Okay, so I think that answers all the questions that we were supposed to find. Determine, reading part B, determine whether the mass settles into a steady state. It does, and we determine what that steady state was. If so, find the amplitude, period, and frequency of the steady state, which we did. Okay, so that wraps up this lesson on forced harmonic motion.